Hello students, in this video we'll prove the fundamental theorem of algebra. So our fundamental theorem of algebra, which is something we learn about in college algebra, states the following. It states if I give you a polynomial of degree n with complex coefficients, given a polynomial with complex coefficients, here we go. So here's your polynomial. P of z is the sum. J goes from 0 up to n of a j, z to the power of j. Now, of course, when you're doing algebra, you always think of these things as like what? With like you plug in x instead of z, but there's no reason I can't plug z into these things as well, right? And so this, of course, is what? This is going to be a0 plus a1z plus a2z squared, all the way up to an zn. And what the fundamental theorem of algebra says, it says that what this can be factored into is this can be factored into a number over here, an. So this is going to be equal to an, right? And then times some roots over here. So you can pull up to an, right? And then you have a whole bunch of roots. Z minus r1, z minus rn. You can factor it like this, right? And so in other words, this says, in a nutshell, that this polynomial, so hence P of z has n complex roots, with the idea that you can also, there might be some multiplicities, right? Possible multiplicities. In fact, in Algebra 1, you're really good at solving quadratic equations, right? You're good at factoring, completing the square. When you take a quadratic equation, that's a polynomial of degree 2, you split and get 2 roots. And you remember from that you might get complex roots sometimes, right? So remember that if you think back to just basic algebra, you say, okay, well, if I look at an equation like this, if I look at like x squared, like let's look at a simple example over here, like x squared plus 2x plus 5 is equal to 0. That's a quadratic equation, right? And you say, how can I factor this? Well, you can complete the square. This is going to be x squared plus 2x plus 1 plus 4 equals 0. This is x squared. Then this is going to be x what? This is going to be x plus 1 quantity squared plus 1 quantity squared. And I'm going to do something silly that you don't usually do in algebra 2, where this is plus what? Plus minus rather. Let's put it as a minus. I don't teach algebra, right? So it's been a while since I did this. Minus, I'm going to write a 2i squared over here, right? Equals 0. Okay. Now 4, of course, what's 2i squared? 2i squared is going to be 4i squared, and i squared is 1. So that's the same thing. Now it's a difference of squares. And this is x plus 1 minus 2i. And then x plus 1 minus 2i. X plus 1 plus 2i equals 0. And I've done this, I've performed this factorization essentially, right? So in other words, completing the square allows me to do this factorization for quadratic expressions like that. Beautiful, right? Of course, if there's complex coefficients, you can do functionally the same scheme, okay? Excellent. But then, of course, we get into an issue when I give you a cubic equation, right? When I give you a cubic equation, you say, well, how do you factor a cubic equation? We've already seen that in the video on Cardano's formula, so I'll make a link to the Cardano video. So Cardano's formula allows you to solve cubic equations. There's a mechanism for solving fourth-order equations. And then the quintic case is really interesting from an algebraic perspective because you get situations where you cannot solve these things by radicals, right? We'll discuss that in further when we embark upon our abstract algebra quest. But nonetheless, this is one of the most elementary things you learn about in algebra is that you can take a polynomial and you can factor it, right? Now, why is that true, right? We don't know why that's true. We're just giving it to us as true. So complex analysis comes and saves the day, right? And so here's the proof of the fundamental theorem of algebra. Proof. So P of z is an entire function. Okay. Why is it entire? It has a valid Taylor series expansion for every z, since it has a valid Taylor series for all z. What is this valid Taylor series? It's right here. The Taylor series terminates, right? So it's valid for all values of z. I can plug in any value I want to this Taylor series, and it spits out a complex number beautifully well. So in other words, this converges for all values of z. Therefore, it's an entire function. So in other words, P of z P maps C into C, okay? Now, let's suppose by way of contradiction, that P of Z was never equal to 0. Okay? Then define Q of Z, which is 1 over P of Z. Okay? This is also an entire function. Okay? And it makes sense everywhere because P of Z is never 0, so I can do it, it's reciprocal, okay? So the reciprocal of this polynomial is therefore an entire function, assuming that P has no zeros, okay? Now I need one small lemma over here. So what's my small lemma? It should be easy to believe, so lemma. Modulus of P of Z tends to infinity as modulus of Z, or just as Z tends to infinity, right? Any way you wish, right? Okay. So how do you prove this lemma over here? Well, the proof is straightforward. So P of Z over Z to the power n is going to be what? It's going to be an. Now I have to assume that an's not 0, right? It's going to be an, and then what? And then everything else over here plus what? Plus an minus 1 over Z, et cetera, plus a0 over Z to the n, right? So now, of course, these terms in modulus get small as Z goes to infinity. So these terms over here get very, very small as Z goes to infinity. They go to 0 as Z goes to infinity. In other words, what that tells me, it says that if Z is bigger than or equal to R, some R, there exists an R, so this is possible, implies that P of Z is bigger than or equal to at least half of an, modulus an over 2 times what? Times Z to the power n. Okay, good. Because if this is going to 0, then eventually this is small enough where it will be at least half the size of that, right? So in other words, there exists an R. This R exists. And so that tells me, of course, that as Z goes to infinity, P of Z is going to infinity in modulus. Easy as that, right? Good. All right. Therefore, if P of Z is going to infinity as Z goes to infinity, that means past R. So now Q of Z is bounded in the region modulus of Z bigger than R, okay? And since that, by virtue of what? By virtue of the fact that P of Z is tending to infinity, right? So in other words, eventually P of Z in modulus is going to be less than 1. So if you're going to be less than 1 in modulus, then Q of Z is going to be what? P of Z is eventually going to be what? Bigger than, 100 in modulus. So that says that Q is going to be what? Less than 1 over 100, right? So in other words, for whatever this R is, I'm always going to be able to beat it by the reciprocal of R to the power n times 2 over an, basically, right? So in other words, Q is bounded in this region outside this disk. And since Q continuous implies that Q is bounded in the compact set mod Z less than or equal to R. So it's bounded over here, and it's bounded over here, right? Therefore, Q is bounded everywhere. And entire. And we know by Liouville's theorem that bounded and entire implies that Q is constant. Okay? Now, if Q is a constant, then so is P. Okay? Now, of course, I have to say that it's a polynomial that looks like this, and it's a non-constant polynomial. If the polynomial is constant, there's no roots, right? So in other words, I have to be a little bit more precise about this. The Fundamental Theorem of Algebra says given a non-constant, right? So we should really say non-constant over here. Non-constant, that's the boring case for polynomials. Non-constant polynomial with complex coefficients, then we can factor it like this, okay? Beautiful. Now, of course, how does this factorization? This just shows me what? I assume that there was no root, and that gave me a contradiction, so there's some root, right? So I know that there exists an A such that P of A is equal to 0, okay? But I can expand this I can expand this Taylor series anywhere, so we know that P of z is also equal to the sum of maybe different coefficients. J goes from 0 up to n of some new coefficients, bj, and then z minus a to the power n, right? And I know that b0 has to be 0 over here because we're plugging in a at 0. So this really starts at 1. J goes from 1 to n of bj, z minus a to the power j. And now, of course, I can factor out z minus a from this, right? So this is going to be z minus a times some other polynomial p tilde of z. And of course, the degree of p tilde is what? Degree of p tilde is now n minus 1, okay? So in other words, I can pull out one root from this thing over here. So if I can pull out that one root, that z minus a, then I can use induction, right? Now induction says I can pull a root out of that thing, I can pull out a root of that thing. And I do this procedure until I exhaust the entire thing over here, right? And so of course, the bn is going to stay in the same spot as the an. So in other words, the an is equal to bn over here, or the bn over here is going to be the last coefficient that's going to pop out. So if you use this idea over here along with induction, you can prove that this factorization is possible, which gives me a very, very, in some sense, short proof of the fundamental theorem of algebra. Now the remarkable thing about this is that this is something that is a purely algebraic statement. It's a statement about solutions to an algebraic equation. That's it. Okay? It happens also to be holomorphic, right? So the fact that the polynomial is also holomorphic is what saves us here, right? Because since it's holomorphic, if it was zero-free, then its reciprocal would have what? Would also be an entire function, right? So I have two entire functions, a function and its reciprocal. Now, what this is showing us is that it's inconsistent if one of those functions is either going to 0 or going to infinity. It's inconsistent that they both are zero-free, right? So in other words, this argument over here basically uses the full sort of force of complex analysis, the Cauchy theory, right? It uses the Cauchy integral formula to get a result from an algebraic result. Very, 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 very powerful technique. The corresponding proof that comes from abstract algebra requires a tremendous amount of machinery to actually develop the machinery that's necessary to do this. So in other words, this in some sense is the more natural approach to proving the fundamental theorem of algebra, and so it shows the true power of the Cauchy formula to get something from algebra for almost for free, basically, out of this calculation. Thank you very much.